Let us start our question here. I want to start here. Just show. Okay. Please draw the diagram. Question states calculate the work done in BTU from process 1 to 2 to 2 to 3. So if I draw this diagram, so it goes from here to here and here to here. So these are the two lines where the process is being uh, completed. So I would say if you do the math for area under the curve, so if you do this, so if I change this, oh, it's okay. So if you take a look, this is shape number 1, and this is a rectangular shape. So what is the area of shape 1? This shape is like this and like this, like this. So it is 15 here. It is 25, 300 here. So so if you do the math, so work done in area under 1 is like a trapezoid. And if you take a look here, these are the two heights, one height number 1, height number 2, and the distance between them is 3.1 minus 1. So I can do like 15 plus 300 divided by 2 times 3.3 minus 1. So this will be the area of figure 1. I will say this one. So about the area of figure 2. This is the figure 2. Okay, this is a rectangular. So I will say rectangle. So if I draw this over here, it's like 3.2. So this is 2.2. So 1.3 is this side. 300 is this. So can you do the math for me and let me know what is the total area? So here there is one thing I want to mention, that you will convert this into BTUs. So conversion, how do you convert from foot pound? So 1 BTU is equal to 5.404 psi feet cube. So I think you can convert it because our answer, it should be in BTU, British thermal units. So what I'm gonna do here. So what is the area, total area? Can you guys tell me total area? And then I will convert it into this is, let's assume this is 1650 psia feet cube. And according to that conversion, this is equal to 5 point. If you divide by this number, psia feet cube times BTU, what do you guys get? Okay, that's not what I have. So let's do it together. So if I have 315 divided by 2 times 2.3, this is the one which I have. Okay, so for this area, 300 times 1.3, 390. So 390 plus 362.25. One thing I want to mention here that I forgot to tell you, that this area needs to be subtracted. Why? Because final minus initial. So it should be negative. It should be 2 minus 3.6. So that's why it's a little bit confusion here. Why am I doing positive? It should have been negative here. So this one, it should be negative. So if you do the math again, so what will happen that 362.5 minus 390, 27. So 27 divided by 5.404, negative 5 point. So this is negative. Actually, I did not write down negative sign with it. So it is negative. Do you guys understand this? So the right answer is, so the major takeaway from this, that it's not the rectangular area to have been final minus initial. I forgot to mention this in the beginning. So I took initial minus one. So final. So if you can, do you guys understand this question? If you guys understand it, please type in yes. If not, then I will explain it again. Let us solve this question. A piston cylinder device, it initially contains 0.07. So initial volume, it is given as and the gas is nitrogen, and initial pressure is 130 kilopascals, and the initial temperature is given 120. I would convert it into Kelvin. The nitrogen is now expanded polytropically. So imagine this is my, I would say, initial point, final point. This is expansion polytropically. question is find the work, the boundary work done. And you already know that in the previous lecture, there were a few formulae. So I'm going to write it down. I'm going to just copy this line over here just to show you which option is better for us in order to solve this question. I would say use this option. Let me erase this portion here. And the answer should be in uh, kilo, kilojoules. Determine the boundary work done during the process. So in order to solve this question, I would say yes. What is V2 and V1? So we can find it out. Look, the mass is not given directly, but look over here, if you apply the gas equation, V1 equals to mR T1. And what is the R value of specific, this is for nitrogen. So if I go back to, I believe I solved this question last time over here, if I remember. R value, this is little blurry, but it's okay. For nitrogen, the R value is 0.2968. And I'm going to use this formula, boundary work, P2V2. And V1 we do have, V2 we do not have, but we can find out V2 by this gas equation. And we do not know M, but we can find out M from this gas equation. So let's find out M from the first gas equation. P1 is 130 kilopascals. P1 it is 0.07. R is 0.2968 kilojoules. I did not convert kilopascal to pascal, so it's just less 0.2968. So please help your professor and tell me what is the mass. In my notes, the mass is 0.078. Do you verify this? Open your calculators and help me. So this is the mass. Okay, let's go move forward. Now, if we know the mass, can we find out what is the volume? I think Sarah is typing something. So let's wait until anyone else who wants to find. It's almost the same. So there is little problem. I think 120, 393. I think this is good. Let me double check in my notes. 0.07 times 130 divided by 0.2968 divided by 390. I get 0.078. So it's almost, maybe you can double check. But let's see over here, if you do the math here, you should be able to get volume, the big V equals to 0.08 637. So once we know the volume, add 2. So we know this volume is known, and this V1 is known, P1 and P2. But what is unknown is N. We do not know what is N. So N can be found from this relationship, P1, V1 equals to P2, V2. So how will you find this out? So let's see P1. What is P1? It is 130 and P2 is 130 divided by 100. What is V2? V2 is 0.08. What is V1? 0.07 raised to power N. So I can do the math here. 1.3. If you take the ln on both sides, this ratio. So let's see if I show you what is ln of 1.3. 0.26 and ln of 0.08 637 divided by 0.07. Okay, then you just divide these numbers. So 0.26. So let me show you. 0.26236 divided by 0.21. I got 1.249. And the value of N is equal to 1.249. And once we know N, we can use this formula just to plug in the values. And then that will give us the answer. What is P2? It is 100 kilopascals. What is V2? It is 0.08. You solve for this, you should get 1.86 kilojoules. This is your answer. Let me go back again. I will start this problem by writing down the formula for polytropic work done by the polytropic process and start finding out the unknowns for this formula. So I found V2, which was unknown, from the gas equation. So you must know how to use the gas equation, how to use this formula, how to use this, how to find out N from the process. This is important. You might you might see such problem in your quiz. So it is better to understand how to find out the index of a polytropic process. Do you guys understand this problem? If you guys understand, please type in yes. If not, then I will explain. Brina says yes. Sarah says yes. These two students are very active, and other students are still active, but they are probably just listening. Okay, that's Magali says yes. Taylor says yes. All right, let's go to the next question. I would show you one more problem, and I will share with you some homework problems today, which you're supposed to finish probably in a few days. Let me decide. So let's do this problem. Let us solve this problem. 1 meter cube of saturated liquid water. So the water is saturated. Is expanded um, isothermally. So if I so this is an expansion taking place isothermal process until the quality it goes until the quality is zero point 0.8. Is saturated liquid. I will say this point. It's not even touching the dry vapor line. It is just somewhere zero point 0.8. So it is just 80% is over here. This is a second state point. Okay, this is V2. This is V1. Now this is my pressure line. So the boundary work done, the constant pressure inside the liquid vapor mixture, it is written as like this formula. So what is the pressure at find out pressure P1 equals to P2 at 200 Celsius. So let's look at the steam table or the water table, pressure table. Sorry, this is a temperature table. Yes, this value is required. This is equals to. So once we know the pressure, can we find out V2 and V1? So what is V1? If you take a look here, this is our specific volume at state point 1. And the gas is, sorry, the water is expanded and it goes to point 2, where quality is 0.8. So remember, for V2, you can find out. And remember, Vf will not change because it's a constant pressure process inside the liquid vapor mixture, so it will not change. I will just write it down like this. What is Vg? It's a little blurry, but I can read it to you. 0.12721 minus VFG is the difference between dry and vapor, a dry vapor and liquid saturated line. So minus 0.001157. So this will give you the specific volume at location 2, and that is equal to 0.102 meter cube per kilogram. And we want to know what is the big V2, because the question in the formula we are using the big V. Why? Because we want to find out the answer in kilojoules. So not kilojoules per kilogram. So that's why we need a big V, or you can multiply by the mass. So how can you find out the mass? So let me show you. The mass, you know that specific volume, big V divided by M. So that means M equals to big V1 divided by small v1, which is Vf1, which is, so big V1, it is 1 meter cubed. So let's do this over here. Yeah, this is the formula. So let's apply it. What is P1 and P2? They are both equal. They are equal to 1554.9. So what is M? M equals to, let me write it down, M like this. So I will just write it down here. P2 and P1, it is 1554.9. V2 is 0.102 minus V1 is 0.001157 divided by. So if you solve for this, you can open your calculators and see what you guys get. But I can try in my calculator. 1554.9 times 0.102 minus. Yeah, this is the in joules. So this is in kilojoules. Okay, 1.3. I would say scientific notations 10 to the 5 kilojoules. Do you guys understand this question? Let me go back to the beginning, how I solved this problem. Initially, the water was at saturated liquid form, and then I used the water table to find out V sub F, which is at location 1. We know the quality at location 2, which is 80%. So we found V sub 2. And this liquid vapor mixture, the straight line tells us that there is a constant temperature, constant pressure inside the liquid vapor mixture. Do you guys understand this question? If yes, please type in yes. If no, you can ask your professor. Do you want to have a mini break or you want to have early release? Taylor says early. Okay, that's good. Okay, I understand. So let's do the next question. Let us do some slides. Give me just 1 second. I have to open my slides here. I think we covered this slide last time, if I remember. Chapter 4, we studied up until, yes, up until this slide. So let us move forward. This slide is nothing but how to derive the boundary work done of different processes: polytropic, isothermal, constant pressure, and so on. The next equation is, the next slide tells us how to find out how to apply the first law, Newton's first law, which is law of conservation of energy. So I would say you can use this equation. And I've been explaining this from the very beginning. Like if we go first lecture, this is the first equation. I wrote down the first law in the first lecture. And this is same slide. It is coming again. Look over here. This slide is telling us the same story. For closed system, this is Qn minus work out equals to change in internal energy. If there is a closed system, you will just increase or decrease the internal energy. But if this is a moving systems are open system, then the velocity changes in convergent nozzles, the velocity increases, so you have to consider the kinetic energy change in kinetic energy as well. And if you want to go from here to here, this is the rate or the power. The same equation you have to do the rate of energy, time rate of change of energy. And then there are individual terms, work done, heat supplied, individual terms. And then this means that it's path dependent. Energy is path dependent. This means the energy is point dependent. Small d stands for point dependent. And work done and heat, they follow, they depend upon the path, how the path of the process is taken place. This is the path. This is what I'm talking about. This is a path. And a point function is a point function in which it does not depend upon the path. Irrespective of the path, they just find out the final and initial values, like kinetic, sorry, we call this internal energy. This is the point function, point dependent. You know what I mean? Okay, let's go to the next slide here. Again, this is telling us the same story. Newton's first law of, I would say, conservation of energy principle, first law of thermodynamics, the Q net in minus W net in equals to the change in the system energy. System would be like maybe water or perfect gas. So this is general. Heat goes in, work is performed, you get this value. We will solve some problems. For a cycle, delta E equals to 0, that's Q equals to W. First law cannot be proven mathematically, but no process in nature is known. So yes, if first law is valid. Now the next equation is this formula. Please write down this formula. We call this as enthalpy. And enthalpy comes from the Newton's first, the first law of thermodynamics, like Q going in, work performed, W. If you rearrange this, you get this at a constant pressure. You get, so H, please write this down in your formula sheet. H equals to U plus pressure times specific volume. This is the flow energy. This is the internal energy. So a fluid moving contains enthalpy. Enthalpy is very important property of a moving or of a fluid. Okay, guys. So this you have to understand. What? How did we get enthalpy from the Newton's? The first law of thermodynamics, which is law of conservation of energy. So, so this is the takeaway. The first law gives us the property enthalpy. And you will see in the later chapter, the second law of thermodynamics, this is law LAW, okay? Second law of thermo uh, entropy, S. This is T, not J, this is T. We will talk more about this. Is just I'm kind of throwing it early, but second law gives us a property name, entropy. The first law gives us a property names, enthalpy. And the formula, I have written both formula in front of you. Enthalpy equals to U plus PV. Change in entropy equals to the heat supplied or heat exhausted or heat exit divided by the Kelvin scale temperature. Okay, guys, so let's do the next slide. The next slide is a different topic, but that is a little different about the specific heats. So specific heats for gases can be considered at two different levels. One is at constant pressure level, one is at constant volume level. The energy required to raise the temperature of a unit mass of a substance by 1 degree when the volume is constant, gets kept constant. And when the pressure is kept constant, this is Cp, C sub P, C sub V, and specific heat energy required to raise the temperature of a unit mass for gases. Cp is greater than Cv always. And so for helium right now it is 5.19 and Cv. And there is another relationship which you will find out later on, that N, or I would say Cp minus Cv, Cp minus Cv gives you the gas constant. And for polytropic process, Cp over Cv is the index. So we will learn more about it. I'm just alluding earlier to you guys. So so this is for air. Air is 0.85. So what is N for air? If you do the math here, let me show you. 0.855 divided by 0.718. 1.1. 0.14. Okay, before I move forward, I want to show you that both of these units are identical. You might be surprised, Professor. Kilojoules per kilogram Kelvin, that is also equal to kilojoules per kilogram Celsius. Why is that so? Because when you increase the temperature, suppose at a constant or for any substance through 1 Celsius, when the temperature rise is 1 Celsius. What is the temperature rise in Kelvin? It's 1 Kelvin. So you will see that sometimes the unit is kilojoules per kilogram per Celsius. The same value you will find out, but per Kelvin, because the both rise and fall, they are same in temperature scales, Kelvin as well as Celsius. So don't get confused if the values have different units, but it is due to the rise and fall they are. Another formula which you should note down here, that delta U total change in internal energy, and delta H equals to Cp delta T. This is for specific. For big U, okay, kilojoules per kilogram. I think kilojoules per Kelvin. No, no, it's kilojoules only. Yes. Okay. And also the internal energy at constant volume and enthalpy at constant pressure, the Cp varies with temperature. If you have a high temperature, Cp would be different than if you have a low temperature, or Cv as well. So they depend upon the temperature. So you have to take the average value. So for air, look, for air, if we are considering two different values, you see at higher temperature, energy U is higher as well as H is higher. So what we do in the problem, usually we take the average of the two temperatures. Suppose a process is taking place from small to high. This is a process, okay, taking place from this temperature to this temperature. You take the average temperature and Cp and average, and then you rather than doing the what we call the integral, you just do the average of the two Cp values. Cp 1 here, Cp 2 here. You take the average of these two. So you see the same form. It's almost the same. You see delta U and delta H. I wrote down this formula already. Delta U equals to Cv delta T. And what is this is average. I would say take the average of the two temperatures. This is between the two temperatures. Delta T is the temperature difference. So I will show you when a problem comes, I will show you again how to solve this problem with two. So they are telling us three ways to find out delta U. So I already mentioned to you that Cp minus Cv equals to R. This is the same relationship, okay? Please write down this relationship. Cp equals Cv plus R. Usually, molar masses, we rarely use this formula, but it's the same formula per kilomoles rather than moles rather than kilograms. So this is a point function. That's why we have dH rather than path functions. It's a point functions. K. I'm sorry, this is not the index, but it's a K value. It's different than index, so I would just say this is a K value. K is a constant of specific heats. Specific heat at constant pressure divided by specific heat at a constant volume. For monatomic acid, it is 1.67. For diatomic, this is 1.4. For air, it is this. I can show you here. This is the R value. R comes from the difference of those two specific heats. So R of air. And the ratio of specific heats at constant pressure and constant volume for air can be found using this relationship 1 point about 1.4. For diatomic acid, this is about 1.4, and for monoatomic, this is 1.6. And for talking about the liquids, specific heats of liquids and gases, we we do not consider as constant pressure, constant volume. We just take one value because the volume is constant and solid volume is constant, liquid are incompressible. Therefore, we have a same specific heat for both constant pressure, constant volume for liquids and solids. I believe C for water it is 4.18, but you can check it. Okay, let's do another slide here. Again, this is just nothing, the same formula which I mentioned earlier, that how do you get delta change in internal energy using this for the solids or liquids. Okay, this is not CV, but just C average. And for H is the same, so it's almost this for H or delta H and delta U, it doesn't matter for liquid or solid. Okay, we have finished these all the slides of chapter 4. So, and I have solved a few problems today. Let's do some more problems to practice these formulae. So let me show you. Let us solve one problem. The question is 1 kilogram of oxygen. So the mass has been given to us. and fluid is oxygen. And it is heated first at constant volume and then at constant pressure. You have to find out the heat supplied. You have to find out heat supplied at constant volume. Amount of heat transfer required when it is done. So heat supplied at constant pressure. So if you consider this formula, look, or the first, let's use the first law of thermodynamics. For first law, Q in minus W boundary work equals to change in energy. Okay, can you guys tell me what is the boundary work done for the constant volume process for this one? What is W boundary? Can you please type in the chat box? The question is the boundary moving in the first case? Yes or no? The answer is to that is it is not moving. So boundary work done is equal to 0. And the total energy is delta U, which is equal to mCV delta T. And what is M? M is 1 kilogram. What is CP? So CV. So let's go to the table. According to the table, okay. It's 0.658. -120 minus 20. So you solve for this, you get about 60. So this is your answer for at a constant volume. Now for the second case, constant pressure. Pressure is constant. And that piston is moving up and down. But right now it is moving up. So Q in minus W equals to delta U. W equals to P dV. Constant pressure V2 minus V1 delta U U2 minus U1. And you know, if you do the math, Q in is required. U2 plus P2 V2. If you bring this on the other side, minus U1 plus P1 V1. So what is this? This is H2, this is H1. And if you multiply Q in at a constant pressure multiplied by M, you get this answer. So what is that equals to? So I already mentioned here that for change in enthalpy, this is Cp delta T. So let's write it down. Change in enthalpy Q in at a constant pressure, it is equal to M Cp delta T. And Cp for this one, it is 0.918. I would say 1.918, 100. About 91.8 kilojoule. This is your answer for Q supplied at a constant pressure. The other one is Q supplied at a constant volume. If you guys have understood this question, please type in yes. If not, let me know. If you have any concern, I will explain it to you. We will solve one last question. Let me solve this question. 66.8. Nitrogen gas the gas is nitrogen at 20 psia. So P1 is 20 pounds per square inch absolute and 100 Fahrenheit. So can I convert it into Rankine? Yes, I can. And initially occupies the volume 1 foot cubed in a rigid container. Volume is constant. When you see rigid means it is no work is being done. Volume is constant throughout the process. And equipped with a steering paddle. So if you have a constant volume and you have some kind of propellers and the paddle, you are doing some like mixing, stirring, paddle wheel. So the work is done on non-nitrogen. W going in, pedal work, pound force, foot. What is the final temperature? So we want to find out the final temperature in this case, and I can tell you that how would you find this out? First law, energy in minus energy out equals to the change in energy of the system. It's a closed system. Don't worry about the kinetic energy. For a closed system is zero. Change in potential energy for a closed system is zero. Only the change in internal energy will be taken into consideration here. So how would you write it down here? So we know that there is no heat being supplied. There is no heat being added. Only the work done is in terms of the paddle wheel. So I would say this is the only work done, work going in, which is this equals to delta U. And what is delta U? You guys already know this formula. Delta U equals to CV delta T, or this is in kilojoules per, but this is the delta U, MCV delta T. So I can write this down as MCV delta T, and CV for nitrogen. So let me take a look here. Let me see if there is another. So if we go to the table 2EA. So let me write down CV value for the table. So open the table here, specific heats. So for nitrogen gas, this is BTU per pound mass per Rankine. So CV, it is 0.177. Let me write down separately so that you will not get confused here. So I can write down, but mass we do not know, but we can find out the mass from equation, gas equation. The R value is 0.071. So, but this is in BTU. So yes, so I'm gonna use the other table for nitrogen. Yes. This table is in a unit which is what we need. This is nitrogen, and we need R value for 0.38. So this is the one which we are interested, this one. So I'm gonna use this into the gas equation. So M equals to P1 V1 over R T1. So P1, how much is that? 20 psia, 20 psia, and V1, it is 1 foot cubed. R value over from the table is 0.383 psia feet cube per pound mass per Rankine. And the temperature T1, it is 560 Rankine. 560 Rankine. This Rankine is cancelled, but this. 0.09325. 0.09325. And CV over here it is 0.177 BTU per pound mass per ranking. And this one, and then delta T. Delta T is final minus initial. Make sure this is in ranking. And that is equal to 5,000 pound force foot. 5,000. So now, if you solve for this, you should get T2 equals to 949 ranking or equals to 489 Fahrenheit. With that, I'm gonna end. So please revise this at home again. You will practice. Thank you for today. I'm gonna stop this lecture now. You have a good